Mhm. So let us see today the divergence theorem and the Stokes theorem. Both are very important in integration. Now, the divergence theorem actually gives the relationship between the double and the triple integration, whereas the Stokes theorem, it is gives the relationship between the single integral with the double integration. So let us take the first one. Let's take the first one as Stokes theorem. Initially we go for divergence and then we go for Stokes one. So the first one is Gauss divergence theorem. Gauss divergence theorem. So Gauss divergence theorem, it states that the it states that the surface integral, the surface integral, surface integral of the normal component of the normal component of a vector point function f bar, vector point function f bar over a closed surface S, over a closed surface S is equal to the volume integral of the divergence of f bar taken throughout the volume V enclosed by the surface S, enclosed by the surface S. So that is it's nothing but the double integral f bar dot n cap ds over the surface S is nothing but the triple integral, which is a volume integral, divergence of f bar dot n cap ds dot n cap. Sorry, it is del dot f bar. It has to be dg because it's a. I'm writing some different thing here. Del dot f bar dv because it's a scalar quantity. So what actually it gives you that the divergence theorem. So if I have enclosed kind of surface, so you consider this, suppose this is your box. Okay, this is the box, which is a closed box, correct? Closed box. Now how many surfaces it is having? So in all there are 6 surfaces, right? This is 1, the bottom one is 2, correct? So I'll call it as S1, this is your S2. Then next surface, we just take it, this one, correct? This is 1, this is 2. So I'll call it as, say, This is your S3. This is your S4 with different colors. I'm drawing it. Okay, S4. And then you can see that the front surface here, okay, and the back one. So the back surface is like this, correct? So this is the back surface. So we have the front one is say S5 and the back surface is S6. So in all there are six surfaces. In all there are six surfaces, and here some field is acting on this. Okay, vector field is acting on this. So what this gives you that the surface integral, okay, for some f bar. So some field is acting on this vector field f bar is acting on all the sides of this, correct? So what this gives you that you calculate the surface integral over S1 plus over the integral S2, okay, same thing, and so on. I'll calculate it for six surfaces, no? So this is f bar dot n cap ds. This is equal to, instead of calculating for every surface, the surface integral, just you calculate the volume integration of del dot f bar, divergence of f bar dv. What is dv? dx, dy, dz. Okay. So very strong result is given by Gauss. So since we are using here divergence property or the divergence formula in this case, the divergence of f bar, so it is called as Gauss divergence theorem, and it is used for the closed surfaces. Okay, like ball. Okay, then box. You can talk about the pipe, which is rigid pipe kind of thing, which is closed one. Okay, nothing is open on any of the side. Cone, prisms. So all these things, these are all the closed surfaces. So closed objects. So for all these closed objects, you are using this divergence theorem, where n cap in this case is a unit normal to the given vector. Okay, so n cap is what? N cap is unit normal to the surface, to the surface. So like I have this surface, okay, this is your, suppose we extend this and we just draw this, okay, and this is your say x axis, this is y axis, and this is your z axis. Then in that case, what is your n cap? So I'm just giving you the brief idea. So this you can see that here we have the negative z axis, z dash, correct? So this n cap to this surface, n cap to this surface is what? Minus k bar. N cap to this surface, above surface, top one, it is what? It is plus k bar because they are parallel to z axis, correct? Similarly, the unit normal to this surface here, what is n cap for this? Because it is negative j y axis, no, here. So that means it is minus j bar. Here it is what? It is n cap is going to be plus j bar, correct? Like you can talk about the front and the rear surface also. So they are along the x-axis. X-axis is perpendicular to that surface. So therefore it will be plus I bar and minus I bar. Right? So that way you can calculate here n cap, because they are all nice two-dimensional surfaces. All are nice two-dimensional surfaces. So that becomes very easy to calculate it here. Correct? Very easy to calculate it here. So here, no one will ask you, since your paper is objective type. So none of them will ask you about calculating for all the six surfaces, correct? But then we can definitely do it for triple integration, correct? So let us move ahead. We take one simple example here, and that will give you the understanding of this topic in this case. So let's take the first example for the cube itself. Okay, so I just take some f bar. We'll not do the verification here, but we'll use this. Okay, so example is evaluate double integral f bar dot n cap ds over the surfaces using divergence theorem, where f bar is say 4xz I bar minus a bar plus say zk bar over the over over the surface S, which is x is equal to 0, x is equal to 1, y is equal to 0, y equal to 1, z equal to 0, and z equal to 1. So what is given to you, these are all the planes, correct? These are all the planes. And you can draw the diagram for this. So this is nothing but a cube. These are x-axis, y-axis, z-axis. So you can see that x is equal to 0 plane, x is equal to 1 plane, correct? So that way we can draw this and we can have it. So my cube is not so nice here. So you can see that this intersecting point is 1, 0, 0. This point is 0, 1, 0. And this point is 0, 0, 1. Correct? So these are all the planes, two-dimensional planes. Correct? And they are just intersecting. Since comma is there, you have to consider all of them. So the surface is bounded by the planes. You can see. So here one can write it down that the surfaces are bounded by this planes. Correct? And they are all coordinate planes. So now what the divergence theorem says, using divergence theorem, the double integral f bar dot n cap ds over the surface S is nothing but the triple integral del dot f bar dv, correct, over the volume V. So what is f bar? Here f bar is given as 4xz I bar minus a bar plus zk bar, correct. So what is my del dot f bar? Del dot f bar is take the partial order derivative with respect to x, which is 4z. Then derivative this is 0 and the derivative here is 1. So we are getting the function as 4z plus 1. Now take the, so we are not going to evaluate for every surface. We'll evaluate directly the relation. Okay, so that relation gives you have to calculate del dot f bar and find out the volume integral of that function. So what is our triple integral of del dot f bar dv? dv means it is dx, dy, dz. So this is nothing but triple integral 4z plus 1. I just write dz, dy, dx. And we have to decide the limits of x. So what are the limits of x? They are from 0 to 1. Limits of y, 0 to 1. Limits of z, 0 to 1. So when I put z equal to 0 to 1, what happens is it is getting projected in, the entire thing gets projected on two-dimensional plane, that is in XOY plane, correct? Then you are taking the limits of y. Once you take the limits of y, it is getting projected on two dimensions to one dimension, that is along the x-axis, and then you put the limits for x. X is from 0 to 1. So that way we are getting 3D to 2D projection, 2D to 1D projection. Okay, 2D to 1D projection. Now we'll solve this integration. So this can be written as, first of all, we'll integrate it with respect to z, keeping the x limits and y limits as it is. So the integral of z is 4 times z square by 2 plus z, that is from 0 to 1 dy dx. So we'll evaluate this 0 to 1, 0 to 1, put the limits. So what we get this as? So this is nothing but 2 plus 1, that is 3. 3 times dy dx. And now we'll take 3 outside and then the integral 0 to 1, integrate it with respect to y, 0 to 1 dx. So we get 3 times integral 0 to 1 dx. So that is 3 times integral of 1 with respect to dx is 1 x. So you put it, so we get the answer as 3. Okay. So this way that becomes very easy once you evaluate the thing. Okay. So here, whenever we have an enclosed surface or on all sides it is bounded one, then the things are very easy to evaluate it, the divergence theorem. Now there can be the one can use in this case the cone, cylinder. Here we are doing it for cube. It can be tetrahedron. Okay, that is coordinate planes with one three-dimensional plane. When you take a surface enclosed by this or bounded by this, we get a nice tetrahedron there. Now let us take the next example here. So this is one. The next is example is evaluate double integral f bar dot n cap ds using divergence theorem where f bar is given as xi bar plus yz bar plus zk bar over the surface of sphere taking sphere as x square plus y square plus z square equal to a square. Let us take a generalized one. So what we have equation of sphere here, correct? So this is the sphere, correct? So the equation of sphere is x square plus y square plus z square is equal to a square. Now you have to use in this case the divergence theorem. So by using divergence, since it is it is closed one, no, it's like a ball. It's a closed surface. So we can apply here divergence. So what is our double integral f bar dot n cap ds? So the relationship between this two is del dot f bar dv. Now what is our f bar? F bar is xi bar plus yz bar plus zk bar. You can see that this is nothing but your r bar. See, this is nothing but your r bar. Correct? This implies f bar is r bar. So what is del dot f bar? Del dot f bar, therefore it is nothing but del dot r bar. What is that? It's 3. Correct? So substitute it. So the right hand side here is triple integral del dot f bar dv, which is triple integral 3 times dx dy dz. See, you can take out this 3 outside. Correct? And what is this? See, it is 1 times. So that means it's the volume of sphere. Correct? So we are getting 3 times volume of sphere, x square plus y square plus z square equal to a square. And what is the volume? So it is 3 times 4 by 3 pi r cube. R is what? A. So this 3 gets cancelled. 4 pi a cube. This will be the answer. Correct? Yes, it's correct. So see, it's very simple. Now here it can be, one can frame it like this also, because this is very simple. So I can write it down 2xi bar plus 2yz bar plus 2zk bar. What is this? Actually, it is 2r bar, correct? It's 2r bar. So just you multiply that, so it is 3 to the 6, 6 times this, correct? And that way we'll get the answer, final answer. So here, with this A, you can have different questions, correct? You can have different questions. Now the next question, little bit different, exactly similar type, but since F bar is different, you'll understand the difference between these two. So evaluate double integral F bar dot n cap ds, where F bar is x cube I bar plus y cube j bar plus z cube k bar over the region of sphere. Okay, so sphere is given as z square equal to 16, correct? Over the surface of sphere, and the sphere is given. So now how to do this? Again, you have to use, of course, the divergence theorem. F bar dot n cap ds is equal to triple integral del dot f bar dv. Correct? So I need to find it out, del dot f bar. So here f bar is what? X cube I bar plus y cube k bar plus z cube k bar. Correct? So what is our del dot f bar? So del dot f bar is nothing but 3x square plus 3y square plus 3z square. Correct? Don't put directly x square plus y square plus z square as 16. That's wrong. That's a function actually, correct? So what is our triple integral? Del dot f bar dv. It is nothing but the triple integral 3 times x square plus y square plus z square times dx dy dz. Correct? Now, when you solve such kind of question, what we do is we use the spherical polar coordinates. Okay, we use the spherical polar coordinates. You can see that we have this sphere. So something like this, correct? Now what I have to do is I have to substitute it in terms of r theta phi. So what is x? X we substitute it as r sin theta cos phi, correct? So put x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And what is dx dy dz? Actually, this dx dy dz you get it from Jacobian, correct? By taking the Jacobian of xyz with respect to r theta phi, the transformed area, transform volume here, correct? So that is r square sine theta. When you calculate that Jacobian, you get this as r square sine theta dr d theta d phi. That way you get. So now how to decide the limits? How to decide the limits? That's the main part. So what we have here, actually, what I'll do, I'll put a knife. Suppose this is orange. Okay. So you just slice it like this. Correct. So let me slice it like this. So you can see that they are not so nice equal width here, but actually it has to be with equal width. So till the point circle, okay, on both sides. So I'm just chopping it down and see that this circle is nothing but like this, correct? This is like this. So here the radius r, and we have this angle here. You can observe that we have x is equal to r cos phi, y equal to r sin phi. These are the circular coordinates. So here angle is phi. So phi will take the value from 0 to 2 pi, correct? Phi will take the value from 0 to 2 pi. Yes. What about R? We have point circle to the greatest circle. Correct? This is your greatest one. So R will take the value from 0 to A. What is A here? Radius 4. It is 16 given, no? So radius is 4. And now we have to decide the theta. These are theta. So you can see here that we have, this is actually your theta every time. Okay. So theta, when theta is equal to 0, it will cover the point circle. Theta is equal to pi by 2, it will cover this greatest circle. And when theta is equal to pi, correct? It will cover like this. So these are all the circles we will cover, correct? This is your theta. This is your theta. Okay, so these are all the theta values. So theta, when it comes to 0, it covers this circle. When it comes to this point, it covers this circle, correct? Yes. So theta will take the value from 0 to pi. So theta is from 0 to pi. Correct? So whenever it is a hemisphere, you can decide the limit that way. Whenever it is quadrant, only first quadrant you have to take. Then that way you have to decide the limits. 0 to pi by 2, it will take all of them. Correct? So here, this is the way you can solve this. Okay. So let us go ahead and we'll complete this question. So here what I have to do, I have to convert this. So what is the value of R? R is taking the value from 0 to 4. Theta is from 0 to pi. And phi is taking from 0 to 2 pi. Here we have R square sine theta. And one more R square is there. Let me take out this. Okay. So what I have is, I have here 3 into R square. X square plus y square plus z square is what? R square. And dx dy dz is one more R square sine theta. Dr d theta d phi. Correct? Dr d theta d phi. So this becomes triple integral 3 times r raised to 4 sine theta dr d theta d phi. And now see, they are all multiplication in multiplication. So I just take the integral of r raised to 4 separately. That is from 0 to 4. Integral of sine theta separately, where theta is from 0 to pi. And integral of d phi separately. There is no term. Correct. And now we'll solve this. So 3 times it is r raised to 5 by 5, 0 to 4. This is minus cos theta from 0 to pi, and this is pi from 0 to 2 pi. Now when you put the upper limit, we get 3 times 4 raised to 5 divided by 5 into minus cos theta. So minus sign, when you take out, cos pi is minus 1 and cos 0 is again 1. So minus of minus 1 minus 1, that is plus 1. So it becomes 2. And here it is 2 pi. Correct. So when you multiply all of them, you'll get the final answer. So that way you can find it out this. Okay. So this way you can solve the question. So whenever it is r bar, that becomes very easy to solve. But when it is going ahead and you have different terms there, so then you have to convert it in terms of spherical polar coordinates. Okay, spherical polar coordinates to get the answer. Now we'll move ahead and we'll see the equation of Stokes. Stokes theorem. Stokes theorem. So this is actually the generalized from Green's lemma. Okay, generalized from Green's lemma, where we have the in Green's we have seen that we can use only two-dimensional surface, but here we can go beyond that and we go for three-dimensional surface. And the Stokes theorem actually it gives the surface integral of normal component of curl of a vector point function f bar, which is taken over on open surfaces, which is bounded by some curve C, that is equal to the line integral. Okay, so that means we have here that the f bar dot dr bar over the closed curve C is nothing but the double integral over the surface del cross f bar dot ds bar, where a ds bar, say a ds bar is nothing but n cap ds. Okay, so whenever I have written there n cap ds, one can write it down that as ds bar also. So here we are using that rotation. Okay, so that means one part has to be open, then only you can find it out that particular curve. Okay, closed curve here. So let us see that the box is open. Okay, you have open box. Then there you can't use the divergence. There you have to use the. So let us draw this. So this is your. Suppose I have this open box. Okay, so open means here you can see that the curve is there, and here you are applying the field, vector field. So instead of, now how many surfaces are remaining? 5 surfaces. In all there are 6 surfaces. Out of that one is open, correct? It's an open box. No lead is there for that. So then we can calculate the surface integral for every surface. So in all we have to calculate it for 5 such surfaces. So instead of that, what the Stokes theorem says, so you can just draw, you can just calculate the line integral for that open curve, correct? So only calculate the line integral, and that is equal to this, that's equal to this one. Now let us take the example based on this. Let us take the example based on this. So we have a nice example for the square lamina or rectangular lamina. So let's take one example. I'll just take it on the other page. So example, evaluate double integral del cross f bar dot n cap ds over the surfaces where f bar is x square I bar plus yz z bar plus zk bar. The region is S is bounded by the planes, x is equal to 0, x is equal to a, y equal to 0, y equal to b, and z equal to 0. So we have to take here planes. So let us have z equal to 0 means I can have it like this, correct? This is my x-axis and y-axis. Now x is equal to 0 is this line. X is equal to a. So here it is by lines, correct? Not by planes, because we are talking about now 2 dimensions. So y equal to 0 is this line, and y equal to b is somewhere here. So the points, this is our rectangular lamina here. This point is 0, 0. I'll call it as A. This is your B. That is A0, this point is C, we call it as AB, and the point D is nothing but it is 0B, correct? And we have defined the orientation here. So the orientation is look like this. This is our curve C, correct? So now we have to find it out this by using Stokes theorem because it's open curve. So using Stokes theorem, what we can do is we can have the line integral. So double integral del cross FR dot ds bar is same thing as the line integral FR dot dr. And that's very simple to find it out. So one can solve it like this. So what we do is we just find it out the line integral FR dot dr bar. So you can see that this is nothing but the line integral FR dot dr bar. Have to follow the orientation, no? So AB, then we have to go to B to C, then C to D, then D to A, right? Then D to A. What is F bar dot dr bar? So here I have to put, so F bar dot dr bar is nothing but your x square dx plus yz dy plus z dz. Here put z equal to 0. So that means dz is 0. So what I get f bar dot dr bar now? F bar dot dr bar will become x square dx because we are putting z as 0. In some cases, it may be given that z equal to 1. So z equal to 5, like that. So there you have to just see what kind of integration you are supposed to get. So what we get this as, this integral is nothing but x square dx. Okay, what I have here, the equation of AB. Equation of AB is what y equal to 0. Put y as 0, dy equal to 0, and put the limits of x. What are the limits of x? We are getting 0 to a. So x is from 0 to a. Next integral is along BC. That is, you have to put the x is equal to a and dx is 0. So I'm getting the integral as 0. Correct? Because you are putting in f bar dot dr bar x as 0, x as a, dx as 0, and that is the only term. In some cases, you may get dy term also. So there you have to just find it out that value, correct? And get the answer. Then the third one is what? Along CD. CD means equation of line is what? Y equal to b. So dy is 0. So that is x square dx. And what are the limits? The limits are from x is from b to a to 0. Correct? I'm going this way. So it is from x is equal to a to 0. Correct? Last one is integral d to a. So equation of that dA is what? X is 0. Put dx as 0. So we get the integral of 0. So see, we are evaluating all the line integral together in one step. And that way we get this as x square dx plus this. So put the integral limits and solve it. So we have x cubed by 3 from 0 to a. This is 0 only. Then next limit is x cubed by 3 from a to 0 plus 0. So you can see that we get this as a cubed by 3 and this has minus a cube by 3. So the answer is 0. Okay, answer is 0. So it's a conservative means, correct. Even you can get the answer with the help of del cross f bar also, where n cap is k bar here. Okay. So that way also you can solve this. That way also you can solve this. Now, so we may have square lamina, rectangular lamina. Okay, so all laminas that is two-dimensional. We can say that the grid kind of thing, simple, only one grid. Yes, so there you can use this and you'll get the answer. Now let us move ahead and we take one more example. So here in the exam, since they are all 2 marks questions, so it may be asked to find it out del cross f bar, and then that integral evaluation you have to do it quickly. So that will be very simple one, which you can do it simply and easily actually. So let us take such a example now. So evaluate double integral del cross f bar dot ds bar over the surface S, where f bar is y I bar plus z z bar plus xk bar. S is the surface of paraboloid. This is the surface of paraboloid. This is the surface of paraboloid. Z equal to 1 minus x square minus y square. 1 minus x square minus y square. Z is greater than equal to 0. Z is greater than equal to 0. So you can see that actually when you just calculate this del cross f bar and putting z equal to 0, putting z as 0, you'll get the surface as, see, when I substitute z equal to 0 in the equation of paraboloid, this becomes 1 minus x square minus y square equal to 0. That means we get x square plus y square is equal to 1. It's a equation of circle, correct? So what we do is we calculate actually this double integral of del cross f bar. So let us calculate del cross f bar, which is I bar, z bar, k bar, dabba by dabba x, dabba by dabba y, and dabba by dabba z. And here we have y, z, and x. So evaluate it. So I bar times with respect to y, this is minus 1, minus a bar times x, it is 1, plus k bar times x and y, minus 1. So we get minus I bar minus a bar minus k bar. This is our del cross f bar. Del cross f bar. Now surface of the paraboloid has a boundary, and that boundary is what? It's a circle, correct? So therefore, the boundary of a plane surface is nothing but when you cut or when you see on z equal to 0 plane, it is a circle. So we'll calculate it over the circle, correct? So you can see that. So I'll call the surface for this, we call it as say S1. I'll call it as S1. So the double integral over S1 del cross F bar into ds bar. So this is nothing but over the surface S1 minus I bar minus J bar minus K bar dot n cap. Now what is n cap here? So you can see that we have here S1 on z equal to 0 plane. This is on z equal to 0 plane, correct? It's a circle. It's a circle. X square plus y square is equal to 1, correct? So therefore, this is nothing but your x square plus y square equal to 1. So therefore, your n cap is what? K bar. Positive z axis n cap is k bar. So therefore, we can write k bar times dx dy. Correct. So what we get this as, because it lies in two-dimensional surface and that is nothing but xy plane. So we get minus of dx dy. When you multiply it, we get this as minus dx dy. And what is this? This is, you can take out minus sign outside, dx dy. We get this as minus of, this is over the surface S1, no? So what is this? This is area of circle. What is that circle? X square plus y square equal to 1. So what's that? Minus pi r square. That is minus pi. This is the answer. Okay, this is the answer. So you can see that the question can be solved very easily. So del cross F bar will be provided, correct? And then this is a very simple thing that when you substitute here K bar, but n cap you have to find it out. N cap you need to find it out in this case. So once you get that n cap, the part becomes very easy because that gives you directly the area, correct? So this gives the area of circle. Okay. So there can be, one can write it as z equal to 4 minus x square minus y square for z positive. It will be what? The circle will be x square plus y square equal to 4. Correct. Or you can have a square. Then what will be the answer? The same answer, it can be written as minus pi a square there. काय नागरे मुद्दामून करता हो. So it will be minus pi a square. Okay. So now we'll move ahead to the next. So as I said, there can be several questions of this type. The only thing is we'll just you must know how to use it. That's the only thing. Otherwise, the rest part is very easy here.